Let's apply related rates to treating some cancer. We have radiation of a spherical tumor can continue to shrink even after the radiation has completed. So this is ideal that you only have to go through the process of getting radiation for a certain amount of time, and that doesn't mean it stops working the moment that you're done with the treatment. After the treatment, it can still continue to work to decrease the size of a tumor. The spherical tumor is expected to shrink by 0.12 centimeters per week. So it's going to slowly continue to shrink even weeks after a radiation session. Find how rapidly the volume of the tumor is decreasing when the radius of the tumor is 4 centimeters. So there's the two numbers we were given at the time of treatment is completed. So and remember that radius and sphere formula because we have a spherical tumor that we're treating here. So our equation that relates them is that the volume of the sphere is equal to 4/3 pi r cubed. And then we're going to take the derivative of this with respect to time. Derivative of 1v is just 1 dv dt. 1 times dv dt is just dv dt on that left side. On the right side, we can bring down the power 3, and we're going to get 4/3 times 3 is 4 pi r squared dr dt. Bring down the power, subtract from the new power, and then we took the derivative of the radius with respect to time. Now we can figure out what we have for our variables and our derivatives. So we're going to do our setup off to the side. We want to look at the original equation has v's and r's. So we're going to get a v equals and r equals, and then also their respective derivatives. So we have dv dt and dr dt when we take the derivatives with respect to time. And let's look at the numbers we're given to see where we can fill it out, whether it's v, dv dt, r, or dr dt. So the first number we're given is that the spherical tumor is expected to shrink by 0.12 centimeters per week. So we want to figure out what number that is. It's definitely not going to be v or r, right? Because it's a rate of change. The spherical tumor is expected to shrink by 0.12 centimeters per week. Find how rapidly the volume of the tumor is decreasing. So we want to know how fast the volume of the tumor is decreasing. That's what we're asked to find. So what we're given must be how fast the radius is shrinking. So if you couldn't tell just by looking at that 0.12, you could read further in the problem, and it says how rapidly is the volume of the tumor decreasing. So we must not know that, which means we know the other derivative. The other hint in this is that 0.12 was given in centimeters per week instead of cubic centimeters per week, right? Any area is going to be a squared, and any volume is going to be a cubed because you're multiplying three things together. So since it's a regular centimeters, it must have been measuring the radius and how it was changing. So we're going to figure out how fast the volume is changing, which is going to be in cubic centimeters per week. Because if the radius is in centimeters, the volume is going to be in centimeters cubed, and our time is in weeks for this problem. And we know the other number here says the radius of the tumor is currently 4 centimeters at the time of treatment being completed. So the radius is 4 centimeters. I'm not told what the initial volume is. I could plug into the original function right here and find out. 4/3 pi times my r is 4 getting cubed for this one. But since we don't need it any place when we plug into our derivative, I'm not even going to continue to find it. So I know how fast this is decreasing, and I want to figure out how that is impacting the volume. So something with this setup is a little off. See if you can figure out what we need to change. So R is definitely 4. DRDT is 0.12, but this is supposed to be decreasing. If I write it as a positive 0.12, then that means their tumor is actually increasing. So be careful on the signs here. I want to make this 0.12 a negative 0.12. We're decreasing the size of the tumor even weeks after treatment. Which is why normally if you get radiation, they give you a treatment plan. They say, hey, we think we're gonna have to bring you back 5 times. But sometimes if you're fortunate enough and it keeps working really well on your weeks off from treatment, your treatment plan of 5 might go down to 4 or 3, which is awesome. So we wanna make sure that's a negative. We're decreasing this tumor, not increasing it with radiation. So our volume, how it's changing with respect to time, is what we're actually trying to solve. So I'm gonna leave that as a dV/dt and plug in the rest, which is going to be 4 pi, and my radius is currently, unfortunately, 4 centimeters, and that's getting squared for the size of the tumor. So we have 4 pi r squared, so 4 pi times 4 squared for this one, and then we have dr/dt. We are decreasing this by negative 0.12 centimeters. So dV/dt, I just need to multiply these out. It's already solved for what I'm interested in solving for. So I can take this and make sure I do PEMDAS or use the calculator, because we have to square before we can multiply. We have 4 squared times negative 0.12 and times 4. We're getting negative 7.68 pi. And that's cubic centimeters per week. Is it okay that we got a negative answer? Yeah, we want the volume to decrease. The radius is decreasing, so the volume overall must be decreasing, which is great for this patient. So we're gonna say as the radius decreases by 0.12 centimeters per week, right? You don't say decreasing by a negative, because 2 negatives cancel out and become positive. So as the radius is decreasing by 0.12 centimeters per week, that doesn't sound like a whole lot, but the related rate is that the volume, you got a negative answer, is decreasing by decreasing by a positive, 2 negatives cancel out, decreasing by 7.68 pi cubic centimeters